I want to try and demonstrate how to do a simple student's t-test today. Typically when we do biology, we have simple statistics that we do, like a standard deviation and a average, mean. But that really doesn't tell the full story about whether numbers are different. What a t-test is going to do is take two sets of data, calculate the averages and variance and standard deviation, and then do a more sophisticated test to tell you if those two mean averages of those two populations are really different. So let's go ahead and just try two sets of data here. Let's just call them set A and set B. Let's suppose, for example, I've been measuring the weights of the students in my classes, and I'll just randomly put in some numbers in here, like so. And then in set B, I'll also put some numbers in here, like so. And I'm going to intentionally, on that last set there, set B, put in more numbers than set A has. Just to show you how many numbers are in here, I'll go ahead and put another column in here so it's kind of easy for us to see. Let's spread this one out. Let's count up the number of items we have in each one. The formula for that is simply count, and we'll drag and select over that. So I have 7 items in the first one, and in set B I have a few more. I have 10 items in there. No problem. Let me just go ahead and show you, by the way, how to do the averages. So average, formula for that is simply average, and we'll drag over those numbers again. 145, and for this one we have an average of pretty close, 138. So they sound pretty close. You might say set B is different than that one. Let's look what the standard deviations are. Formula for standard deviation is STDEV. Let's put an equals sign in here, STDEV, and let's drag over those numbers there. So plus or minus 32, and in this guy we have a standard deviation of 14.1. So the first set A has 145 plus or minus 32, and the second set is 138 plus or minus 14. If you just stopped there and did those statistics, you might come to the conclusion that there really is no statistical difference between set A and set B, because the averages plus or minus the error bars would really overlap. However, we're going to do a more sophisticated calculation by considering what the variance is and how many items are in each one. And that's called a t-test, and here's how you do it. First of all, we have to come up with a null hypothesis. What is a null hypothesis? Well, it's a starting point. And typically in biology, the null hypothesis says there's no difference between the two sets. So our null hypothesis will be set B is statistically the same as set A. We're going to go ahead and try and prove that. So here's how we do it. We'll do a t-test. Equals, and let's go ahead and insert in here a function. Now this is going to be a statistical function. So I'll bring up my statistical functions here, and let's scroll down here. We're going to come down to t-test. There we go. Okay, t-test comes up. Now the t-test is actually going to ask us for 4 different pieces of information. First piece of information, array 1, is simply what numbers are being used. Let's scroll over those. B2 through B8, they're in there. Array 2, that's easy here. And that's C2 through C11. No problem here. Now the last 2 things we're asked for are tails and type. Okay, tails. If you would take the numbers in a normal distribution, you should see a bell-shaped curve, and the 2 extremes on the right hand and the left hand would be considered to be the tails. In this case, we have a two-tailed test. Why is that? If you know that set B is going to be different than set A by moving the mean in only one direction, it'd be a one-tailed test. We don't know that that's true at all. Could move in either direction, so we're going to select two tails. Typically, we'll always use a two-tailed test in a biological experiment. Last thing we have to put in here is type. Well, in this case, we have unpaired data. What does that mean? It means that if you look up here, the data that's in this row, for example, 122 and 155, are independent of each other. And the numbers in the next row, 122 and 145, are also independent of each other. They're unpaired. What might be paired data? Well, suppose I had a classroom of students and I wanted to see how their weight was going to change over 1 month. That would be paired data, because if I was taking two different sample points, I would be measuring each student against himself. I'd measure Tommy at time 0 and Tommy after 1 month. Those two pieces of data would be paired. That would be dependent data. We have unpaired or independent. The next thing is, are the sets of data equal? Obviously they're not. We have two sample unequal variance. If you look down here, that would be choice number 3. Typically we're going to use number 3 all the time. Let's go ahead and enter that in there. Now if you look up here, it gives us our t probability. I'm going to go ahead and clean that up, by the way. I don't like the fact that it's got all those decimals. Let's go ahead and just make it down to 2 decimals. Great. 0.60. The p-value here from our t-test is 0.60. That is the probability that our null hypothesis is true. Now, typically in a biological test, we would use a p critical value of 0.05, at 5%. If anything is less than 0.05, we would reject the null hypothesis. If anything is greater than 0.05, we would accept it. 0.60 is much, much larger than 0.05. We would accept our null hypothesis. That is, we would say there is no difference statistically between set B and set A. Now that's one way you can do it. There is another way you can do all of this together that's much faster. And that is, just give myself a space over here, by going up to Tools, and if we go to Data Analysis. Now, if you don't see the Data Analysis menu option there, it's because you haven't done the add-ins here, so you might want to do that first, but mine's already in there. Let's go to Data Analysis. If we look down at Data Analysis, you can see there's a whole bunch of t-test options, and you would select the one which applies best to your data. Now I said we have a 2-sample unpaired. We're not going to do paired, so it's 2-sample unpaired. And they were unequal numbers in each one, so that's the one we would select. I press OK. Once again, visible variable range 1. That would be your first set of numbers. There we go. This one here, the second set of numbers, let's go ahead and take those and put those in there. You can see that it already has 0.05 as our critical value that we're going to look at. So really, we're all set to go. I'll pick OK on this, and it automatically puts in this table in here. Let me make this a little larger so we can see what's going on here. Here's our results. So the mean was 145. And 138, just like we saw. This doesn't give us our standard deviation, but it does give us our variance in here. Observations, fantastic. And once again, you can see that our statistical number here is right down there. For our probability for the two-tailed, 0.59, rounded off to 0.60, just like we had before. And we were going to use 0.05 for the critical value. Obviously, it's much greater than that. So there we go, we're already done. And that's how you quickly decide whether the averages of two means are statistically different from each other.